Hey everyone, we're going to take a look at weak acid and base equilibrium problems. These are going to work similarly to the case of EQ problems that we did earlier, where we have to remember that we have products over reactants. But there are a few other things that we need to take into consideration. Okay, it says because weak acids and weak bases don't ionize 100%, they form an equilibrium between the reactants and products. Okay, so remember strong acids and strong bases, those ionized 100%. Okay, and I always said, oh, we'll talk about weak acids and weak bases later, and to find out exactly how much they ionize. So that's what we're going to start looking at now. We do need to understand the symbols Ka and Kb are our equilibrium constants. We're going to use Ka for acids. We're going to use Kb for bases, but it's going to be the same basic idea that we talked about earlier when we did K sub EQ. Okay, we're still going to have an expression, and we're still going to do our products over our reactants. Okay, this is one last thing. The larger the Ka or Kb value is, the more product there will have been made at the end. Okay, so therefore it's going to have a higher percent ionization, and therefore the acid or the base is stronger. Okay, so remember, the greater the percent ionization, the more or the stronger that acid is. So we need to be aware of these two formulas. The percent ionization is H plus over the concentration of H plus over the concentration of the acid times 100. And base is basically the same thing, but it's the OH minus concentration. Now, here is a problem that you can do in your own notes, if you'd like, or a problem at least to reference to. We're going to go ahead and take a look, however, at this problem. It says, what's the pH and the percent ionization of a 2.5 molar acetic acid solution? So what we need to do now is we need to go ahead and write out our reaction. So for acetic acid, we have HC2H3O2. Now that's going to dissociate. We're going to do a double arrow since it's a weak acid. It's going to dissociate into H plus and acetate ions, which is C2H3O2. Oops, not up there. O2 minus. All right, so now if we remember back to our rye problems, this is very similar to rye. We've got reaction, initial concentrations, and ending concentrations, but we've also got the C in here as well for the change. So let's go ahead and fill out what we know. We know that we're starting off with a 2.5 molar acetic acid solution. If I'm starting off with all acetic acid, I have no H plus and I have no acetate ions. Now, my change is going to be how much of this concentration, how much is going to go down, okay? We know it's going to go down by some amount. We don't know what that amount is. So right now, I'm just going to say that this is going to go down by some amount A. So I'm going to say that this is minus A. Well, since this is a 1-to-1-to-1 ratio, if this is going to go down by some amount A, then that means that H plus and acetate are both going to go up by some amount A. So now I need to determine what my ending concentration is. Well, 0 plus A is A. 0 plus A is A. 2.5 minus A, the only thing we can call that is 2.5 minus A. So now my Ka expression is going to be, remember for our K expressions, K sub EQ and all that, we're going to do products over the reactants, okay? The concentration of the products over the concentration of the reactants. So my products are, I've got, okay, my pen's doing something weird here. I don't know what it's doing. Okay, so I've got H plus, all right, we're just going to fight through it. So I've got H plus, oh my goodness, I can't deal with that. Hold on. All right, I'm going to do my Ka expression down here. Okay, so I've got Ka equals, I've got the concentration of H plus times the concentration of my acetate ions, C2H3O2 minus. Now, I'm not going to put, oh, minus needs to be in here. I'm not going to put my any sort of squared or cubed or anything like that because in my reaction, this is all 1-to-1-to-1. I'm going to put that all over my only reactant, which is HC2H3O2. All right. Now, there's a key issue coming up right here. Actually, there's a few keys. First off, we need to understand what is Ka. If you've looked at the back of your notes, you've seen this big chart back here, okay? And you've got Ka values. So I'm dealing with acetic acid, so I see that the Ka for acetic acid is 1.8 times 10 to the negative 5. So you'll need to refer to this chart in order to find out what values you have. So I've got my Ka is 1.8 times 10 to the negative fifth power equals, well, H is A, acetate is A, so I've got A times A, which is A squared. Okay, now, something that we need to be aware of is that this value for A is going to be a very small number, something times 10 to the negative 3 or 10 to the negative 4, maybe even 10 to the negative 5. So what that means is that if I do 2.5 minus a really small number, it's still going to pretty much round to 2.5, okay? That's an important concept to understand because that's going to make our math a lot easier. So what we're going to say is that for 2.5 minus A, we're going to say that A is negligible, okay? We're going to get rid of it. We're going to say 2.5 minus a really, really, really small number is still 2.5. So I'm going to do 1.8 times 10 to the negative fifth equals A squared over 2.5. So now I can multiply both sides by 2.5. Cancel, cancel. And so I get that A squared equals 2.5 times 1.8 second E negative 5. And I get that this is 4.5 times 10 to the negative fifth. Okay? And so now I need to take the square root of both sides. And I get that A equals 4.5 second E negative 5. Oh, square root of that. 0.0067. 0.0067. Now, why did we do all this? Okay, remember, my question asks, what is the pH? How can I find the pH if I've solved for A? Well, remember, A is also my H plus concentration. If I know my H plus concentration, all I have to do is take the negative log of that number, and I'm going to get my pH. So when I put in second log of that number, I get a pH of 2.17. Okay? My Ka, or excuse me, my percent ionization, all I'm going to do for that is I'm going to do, okay, we're not messing with that. We're going to do the H plus value over the acid value. Concentration times 100. Okay, so my H plus concentration is 0.0067. My acid concentration is 2.5. So I'm going to do 0.0067 divided by 2.5, enter, times 100, enter, and I get that the percent ionization equals 0.268, 2.268%. So we remember that a strong acid ionizes 100%. Okay, acetic acid only ionized 0.268%. Okay, that's a far cry from 100%, but that's what makes this one a weak acid. Okay, we'll take a look at another one of these problems in a bit.